All right, I will begin with a word of prayer. I think it's time, right? And then some. Here we go. Heavenly Father, we thank you again for your many blessings. Help us to glorify you what we do and just understand what we need to understand before test for it, Lord. In the name of my prayer, Lord Jesus. Amen. You guys have any questions about anything in particular while I'm loading stuff up here? All right. So would you guys like to look at first the math battle, the missions, the quiz 11? Maybe we'll start with quiz 11 once I find it here. So this test is on what? It's on obviously like indefinite integration, definite integration, FTC 1, 2, and 3, net change theorem, calculation of areas, calculation of volumes, and then of course the problems that represent these ideas on missions, what, 9 and 10 and 8 also, right? All right. Let me start with quiz 11, if I can find it. All right. So here it is. My apologies, I use the printer scanner copier thing in interdisciplinary, and it always puts these vertical stripes in here. Maybe I'll go back to the math department and use theirs doesn't do it for some reason. So here, to reiterate, the acceleration is the derivative of the velocity, so you just take dv dt, which is 2. That's that. Velocity is the derivative of the position, so we have to integrate to find position. So the integral of 1 plus 2t is t plus t squared, because 2 over 2 is 1. We had a constant to fit the initial condition. Here the initial condition is given, the initial condition at time 1, x of 1 is given to be 2, so we get 2 is equal to 2 plus c, therefore c is equal to 0. We get to position t squared plus t. And a lot of you got that, so that's good. A lot of you got that. A few of you got problem 2. So here we're supposed to find the area bounded by that and that. This is a lot like a homework problem where we had 1 minus y squared and y squared minus 1 in the homework. Very similar problem. Anyway, so the picture looks something like that. It's a parabola that opens to the left and to the right. There's a common area between those. The points of intersection given by setting xl equal to xr. I work out the algebra, I get plus or minus 2, so that's why I'm going to integrate from minus 2 to 2. Now I look at this is an even function, right? So for integrating an even function around a symmetric interval of the origin, I can just double it. So that's what I do. I double the integral and I go from 0 to 2 instead, because that makes the calculation easier. I also factored a 2 out from the integrand, so that gave me 4 times that, which works out to, I think, 64 over 3. But I could be wrong. Oh, that is it. So, any questions? So one of you is asking me, do we really need to draw the pictures? Can't we just write down an integral formula? And the answer is no, you need to draw the pictures, because otherwise you're just going to get it wrong. And also I do want you to draw the pictures. So, This problem 3, I don't think anybody here got this correct. Some of you were closer to correct than not, but nobody quite got this one right. And so here we have the solid of revolution formed by rotation region bounded by y equals 1 plus x squared and 1 plus x. So 1 plus x is the line, 1 plus x squared is the curve, and between there you got a little sliver, right? If you rotate that around the x-axis, it gives you some kind of, I don't know what to call that thing, but some kind of like flying saucery thing with a hole in it, like a flying saucer donut maybe. I don't know. You can see all these things as donuts if you look hard enough at it, whether or not you're hungry. And anyway, so the inner radius is given by the parabola, and the outer radius is given by the line here. And so the volume for the washer is pi times r out squared minus r in squared, which is this minus that. Probably if you guys made a mistake here, in all likelihood it happened right in this algebra. If there was a place to make a mistake, more than likely, more often than not, it happens right in this area right here. So you have to FOIL that out. It gives me x squared plus 2x plus 1. To FOIL that out, it gives me x to the 4th plus 2x squared plus 1. I take the difference. That minus has to go on all three of those terms. So the ones, they be canceling. And then x squared minus 2x squared. I'm a dummy. Like, look at this. Why did I simplify this, you know? Like, come on, man. Look at that. This is stupid. Why did I do that? I mean, it's not wrong. It's just not right, you know? I mean, it's not as lazy as I could be, right? It's much simpler to combine the 2x squared terms and go from there rather than, I could have 3 terms when I have 4, you know? Anyway, so I integrate, and that gives me a third plus 1 minus a fifth minus 2/3. And that works out to 7 pi over 15, so, which nobody had. All right, so there's that. Any questions? Oh, okay. Math battle. Let's look at the math battle. And I will post the solution to math battle 4, in Canvas here, hopefully right after class. Again, my apologies for the stupid line in the scan. It just does this. Integral dx, x plus a constant. Integral of cosine, sine x plus a constant. Integral of sinh, cos x plus a constant. Integral of 3 to the x dx, 1 over log 3 times 3 to the x plus a constant. These you should all have memorized. Dx over the square root of x, integrate, that's 1/3 x to the minus 1/2. So you add 1, minus 1/2 plus 1 is 1/2, 1/2 divide, and what? Oh, I was about to say, where's the 3 coming from? Oh, it's in the problem. So, so I get 2 over 3 times the square root of x plus a constant. This one here, do algebra. That's 1 over x squared, and that's x to the minus 3/2. This integrates to minus 1 over x. This integrates to, what's minus 1/3? Minus 3/2 plus 1 is minus 1/2. Oh, yeah. So minus 1/2, and I've divided by minus 1/2, it's multiplication by minus 2. So I get that, yeah. This one here, like I said, this one here is a little bit tricky, but there's a standard trick I use anyway. I add 0. Or you could do long division if you don't like this. You could do division. Division will rewrite this improper fraction as a proper fraction plus a number. So it's 1 minus 1 over x, 1 over 1 plus x squared. And that integrates to x minus inverse tangent. The next one down there, that's just minus cotangent. That's a basic integral. The definite integral here is just going to give me a third minus a half, which is minus a sixth. And let's see here, this one, watch out for the absolute value. Absolutely need it. So natural log the absolute value of minus 2 minus the natural log absolute value minus 3, which is log 2 minus log 3, which is a negative number. That makes sense because this is the area under the reciprocal function between minus 3 and 2. And if you were to graph the reciprocal function, if you were to graph the reciprocal function, we're finding the signed area under the graph, right? Here's the reciprocal function, looks like this. And we're going from like minus 3 to minus 2, let's say. So it's this area right here we're calculating. Should that be negative? Well, yeah, that should be negative. So that makes sense that the answer there is negative. Problem 2. I make a u equals x minus 3 substitution. I change the bounds. The bounds become 0 and 1 rather than minus 3 and 2. du is dx, so I just get 1/9. The next problem here, I make a u equals to 3 log x substitution. So that makes dx over x equals to du over 3. And then I've got sine u du. That integrates to minus cosine. The third rides along. And then I undo the substitution. There's that. This one is a u equals minus x squared substitution. And so my du is minus 2x dx, which brings a minus out here. The 2x and the dx are in the du now. So that integrates to this, which gives me that. Let's see here. Important principle. Don't shackle yourself to using the same u substitution for the whole expression. Right? You can make different u substitutions for different parts, you know? It's important to have the idea of dividing and conquering for integration. You must subjugate your foes. So u is 2x plus 3 for me. That takes care of the first fraction. W equals to 1 minus 3x takes care of the second fraction. And as you can see, I have built it. I have put a 2 and a 3 there to make it easy. Because du is 2 dx and dw is minus 3 dx. So I just get du over u and dw over w, factor the minus out, and there you go. So don't forget your absolute values. Those are important. You guys can jump in at any point if you got a question or something, right? This one here, if we let u equal to cosh, that gives us du over 4 plus u squared. But we know what to do with that. We factor the 4 out. And then we make a w equals u over 2 substitution. So I get 1/2 dw over 1 plus w squared, which integrates to 1/2 inverse tangent of w plus a constant, which then, going back to my cosh and u, gives me cosh x over 2. Excuse me. I'm not annoyed with you guys or with this cough because we are getting really close to graduation. So I feel like odds of me having an excuse to not come to graduation are very high. So it's very exciting. You got to look at the bright side, you know? Let's see here. I should find some AI software to go back through all of my lectures and delete all the coughs from like the last third of the semester, you know? If the engineers come to me, I need a term project, can you suggest a project? I'll be like, every year in the spring semester I get sick for the last third of the semesters. I'd like for you to go back over the last 10 years of videos and like delete all the coughs. I usually make suggestions. The engineers come asking me for like term projects for their capstone course or whatever. They usually respond to me as like, we can only do legal things. And I'm like, oh. So most of my requests involve, I'd like a master key so I could get wherever I want to on campus, that kind of thing, you know. Certain doors won't open. It's really annoying, you know. It would be handy to have like a universal pass. Surely they could 3D print it, you know. There must be a way. So here is the dreaded FTC Part 3 problem. I hope we are all understanding we do not actually do the integral. We simply take the integrand, evaluate it at the upper bound, multiply by the derivative of the upper bound, subtract the integrand evaluated at the lower bound, times the derivative of the lower bound. That's all there is to it. What? What do?
I was going to say, what's the answer?
What's the answer?
Well, that's a continuation of it. There's 2 lines.
Oh yeah, they're both of those are the answers. That's the answer. I just couldn't fit it all in one line because it's lengthy. I mean, I guess I could have, but I had to squish it, so I didn't want to squish it. Yep. Look at that. All I did though was I took the integrand and I plugged in x squared and I plugged in tangent. That's all I did. And then the derivative of x squared is 2x, and the derivative of tangent secant squared. So that's all that's going on there. You guys always, so many of you always want to find a way to make this problem more difficult than it actually is, right? Here, let's see here. Calculate the area bounded by blah and blah. So there's the picture, y plus 1, y squared minus 1, looks like that. So you got a parabola which opens to the right, sideways, and the line. I find intersection points of minus 1 and 2. My dA is the right x minus the left x times dy. Why am I using y for my integration variable? It's because of the picture, right? If I didn't draw the picture and I tried to integrate something in x, it would be total nonsense. So we really need to draw the picture to be sure we know what we're doing. So anyway, I have to integrate. Oh, I'm sorry, I didn't white that out. Integrate this from minus 1 to 2. I can't do my doubling trick because it's not symmetric, so I just have to just do the integral, which I do here. Bop, 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 and whatever that is. 9/2, apparently. This one here, I started to try to find set up the volume of revolution for the region bounded between the parabola, which opens up, and that line. And I got about that far into it. I found points of intersection minus 1 and 3, great for x. And then I realized, oh, I really don't want to use washers for this, because if I used washers, I'd have to split into two cases. I'd have to have like this case down here and that case up there, and I don't want to do that. So shells is a better choice here. So if I use cylindrical shells, 2 pi, the radius, so this is a rotation around x equals minus 2, so the radius is actually x plus 2 here. So 2 pi r that times the height gives me the area of the cylindrical shell. I just laid it flat, and the thickness is dx for the cylindrical shell. So I get this. This is my setup, and yeah. Uh-huh. Because all right. So we'd have, looking at the washer up here, like that. Right? Thickness would be dy, great. But, you know, this is your Rn, right? And R out, right? How about down here? What defines the inner and outer radius for the washer down there? See, at the top, the line gives us the inside radius, and the parabola gives us the outside radius. But in that blue case that I just drew there, it's, you know, the parabola has to give us both the inside and outside radius. So I'd have to work it out and get like a plus square root and a minus square root, something like that. I don't know, it would be a pain to figure out what exactly the inner and outer radius would be in that context. So it's just easier to use shells here. Because with shells, I have the same top and bottom y at every possible shell. You know, the line is always giving me the top, the parabola is always giving me the bottom, and the difference between the y for the line and the y for the parabola always is giving me the height of the shell. Whereas here, I'd have to find the formula for xr and for xl. Now they're both coming from this y equals to x squared minus 2 formula, right? So my x squared is equal to y plus 2, which would give me xl is equal to minus the square root of y plus 2, whereas xr is giving me the square root of y plus 2. So my left x and left r, I'd have to break up and I'd have to find that square root, that would be my right, that would be my left, and I could do it. I just don't want to. It's easier to just do one shell integration. Yeah. So these were unfriendly advice. I said washers or shells will work. As I was warning you guys in the math battle, like, that's not good advice. That's unfriendly advice, is what that is. Let's see here. And then this one, we've got y equals x, y equals 2x, and x equals to 1, bounds and area. So it looks like that triangle there. And we're supposed to rotate around y equals minus 1. So I used washers here. And yeah. So my inside radius and my... So like the inside radius, see, since we're rotating around y equals minus 1, I do 1 plus yb for the inside radius, and I do 1 plus yt for the outside radius. And again, I have to be careful to actually square these out and distribute the minus to all of them, otherwise I'll be wrong. But anyway, works out to 2 pi. Although I didn't ask you to work this one out. I just worked this one out because it wasn't too bad. Yeah? Mm-hmm.
For this problem, you could use washers or shells, correct?
Yeah, you could use washers or shells. But if you used
It's not as horrendous as
shells would be a bad choice here. Shells would be a bad choice because if we did shells, we'd have this to here like that, but then down here the shell would hit it like that. So the shell method we'd have to break up into 2 cases for this one.
Oh, also.
Yeah. So in both cases, there's a better choice. Washers or shell. In other words, my advice at the start of this problem is just complete nonsense. I mean, it's not logically incorrect, but in terms of like the actual calculation, it'd be a pain to do shells here. Yeah. Now, on this kind of question, so if I asked you just to write an integral, you don't have to calculate, right? In that kind of problem, I don't actually expect you to do this. So if this was the problem, I would have been fine with you going up to star and just integrate, like integral from 0 to 1 of this expression is the volume. That would be a perfectly legitimate setup if I have this kind of question on the test. Like I don't expect you to simplify the integrand for this kind of question. I'm just simplifying it because I wanted to calculate it. All right, so like don't, okay. Now if I say simplify the integrand, then simplify the integrand, right? But except for that instruction being there, you're free to not do that. Problem 7 was kind of anticlimactic. So I'm like, well, I can say a equals 0, b equals 4, delta x is 4 over n, and that will make this integral of sine pi x dx, which integrates to 0. So now that's not the only way you could do it. You could have seen this as, you could have put a pi in your bound, right? And you might, if you put pi in the bound, you'd end up with like a 1 over pi for the delta x. You can either, there's not a unique way to identify a given infinite sum as an integral, okay? So you could, even if you don't have exactly this, you might still be right. We should all agree on 0 though. Like that should be a common feature of all our solutions. This one here, I used a trick. You may not remember this. I didn't spend a lot of time talking about it, but there is a super cool antiderivative for the absolute value function, which is u times absolute value of u divided by 2. Like that's an antiderivative for, where'd that minus come from? I think that minus is also supposed to be, where'd that minus come from? What the what? Oh. Notice the bounds. U of 0 is 3. U of 3 is 9 minus 12 plus 3, also known as 0. So when I change the bounds to the u variable, 0 goes to 3 and 3 goes to 0. To flip them like this, that's where the minus came from. So I flipped the bounds, so that gave me the minus. That's where the bounds is where it come from. How else would you do this problem? There's a time, a less simple time, a time where I knew less, where I would have had to break down the absolute value function, find out where it's positive, where it's negative, and split the integral into cases. Do those cases. And sometimes you have to do that, all right? But not through this one because I've got this sneaky formula. That was kind of the point of this problem, is to showcase that formula for you. Now we've done that. I changed this to a cube. The reason for that was not having a cube makes this a Calc 2 problem, not a Calc 1 problem. But with that cube there, this is cosh squared times cosh. So if I let u equal the denominator, I can make that du the cosh theta d theta, which gives me cosh squared du. But cosh squared is just a sinh squared waiting to be rewritten, you know? Because cosh squared is, of course, just 1 plus sinh squared, which is 1 plus u minus 3 squared. So I get this, and then FOIL that stuff out. We have all that. And so, yeah. Was this a hard problem? Absolutely. Is this about the hardest kind of question I can ask integration-wise? It's getting there. It's pretty much it. This is kind of at this is at the ceiling level for our altitude. Something like that. Maybe this is also up there at 90,000 feet. It does require some finagling. So the opening move is to make our fraction proper. So x to the 4th over x squared is an improper fraction. We use long division to rewrite it as a quadratic, a quadratic plus a proper rational function. What I mean by that is the numerator has strictly smaller degree than the denominator. Okay, so this polynomial piece out here, we can integrate that. That's not a big deal. And this over here, well, I complete the square. All right, and completing the square tells me, yeah, well, I gotta think about x plus 3. So once I see that, I create an x plus 3 here by adding 3. Now, if I add that 3 there, that's like adding 180, right? So I have to take 180 from this. So 299 minus 180 is 119. The key thing here is if you multiply this back out, you get back to here. Now, why did I do that? The reason I did that is so that I'm thinking ahead. I'm thinking ahead to the next step where I'm going to make a u substitution for the denominator, and whatever else is going to go into an arctangent integral. So the u substitution for the denominator is this. I make a w actually. W equals to x plus 3 squared plus 4. Oh, excuse me, I can't do math. U equals to x plus 3 squared plus 4, which gives me du over u with a minus 30. And a 119 over 4. I factored the 4 out because I know I want to make this an arctangent, an inverse tangent integral. So I got to factor that 4 out to get a 1 here. 1 plus the w squared. And that gives me this. And then I undo the substitutions. And lo and behold, there's your answer. Problem 11, I fell asleep. So sorry. I will hopefully have the solution to problem 11 posted later today. All right, guys. How would you do problem 11, though? It's just like we did the square pyramid, the rectangular pyramid, and the cone. The issue, and the thing that's going to take me a minute to work out, the central thing here that has stopped me from figuring it out yet, the thing that stopped me from just writing down the answer cold, is that I have to stop and I have to figure out, what's the area of that, I need to figure out what's the area of a pentagon. Well, maybe not A, let's say side length L, How do you figure that out? What's the area of this, right? So I'm going to have to think through that. The way I would think through that would be to figure out the area of like a typical triangle, and then I'd multiply that by 5. What's the angle inside there? What's 360 divided by 5? 72. Is that right? Or am I wrong? What's 72 times 72 times 5 is what? 350 plus 350 plus 10? I think that's right. So that's 72 degrees. And this distance is L. So if you know a triangle has side length L, and this is 72 degrees, and you know these angles are equal by symmetry here, right? 180 less 108, so those are both 54, right? So these guys both got to be 54 degrees, if I haven't made a stupid mistake. So if you know all of the angles in a triangle and you know the side length, you can figure out the area. And once we do that, then we'll have the formula for the area of a pentagon, and then we can go back to our usual methods. Yeah. This is not an easy question. This is definitely in the realm of bonus, you know. All right. Mission 10 solution. So let's see here. Let me look at what do I want to talk about? You want to talk about 386? Okay. So here we were taking this area bounded by y equals 1 over x equals 1, and x equals 2, and rotating it around the x-axis. So I use the method of washers here, which in this case is just disks. My volume of my typical disks, pi r squared dx. The r is given by y, so I end up with pi over x squared dx, integrate from 1 to 2. I get pi over 2. Perfectly good test question. Like, this is a great test question right here. This is a pretty easy one. It's a nice question. It's not too bad. It's not the greatest test question, because one of the things I'm trying to test with these things is finding points of intersection. Like, that's a big deal. And so, like, almost most of these had, you know, finding points of intersection. So, listen, I think I've talked a lot about volumes and revolution, washers and shells today. I'm going to stop talking about. You guys can look at these solutions. If you find a mistake, don't be too surprised. I was pretty tired when I made these solutions. So, like, if you feel like something's wrong, email me. You're probably right. The test is not just about this, right? The test is actually probably, honestly, more about mission 8, if I remember right. Where's my mission 8 gone to? Well, I did give it back to you, but where's my solution? Well, I did post a solution, didn't I? One moment, let me find it. So by the end of the day, I should have all of the solutions to all the quizzes, all the solutions to all the missions, all the solutions to all the math battles. Pretty much the solutions for everything this semester should be posted by the end of today, except for, obviously, the solution to test 4. I can't put that out there yet, right? You'd be like, maybe you're like, yeah, you could. Well, we got class tomorrow, that's for sure. Oh, after the test. Well, I don't think we're going to have class most days. Maybe we should plan to meet like one more time after test 4 to just talk about what to expect on the final exam, that kind of thing. You guys probably would like me to do that, right? One day? Maybe the last day of classes we'll meet again. Sound like a plan? Yeah. I'll make an announcement with this, but yeah, we will not have class Friday, and I don't think we'll have class Monday. Well, I made an announcement about that, and I don't remember it. You know, that's why. See, what you guys don't understand is I make announcements for myself as well. Oh, man. Solution to mission 8. There it is. Hiding in plain sight.
Monday, May 6th.
Monday, May 6th. That sounds right. 1 to 3?
Yeah.
I remembered. Come Come on.
Did you set up like a study guide or something?
The whole course is a study guide. You guys are funny.
Set up like
Every day in this class is a study guide. Let's see here.
refresher or something. Set up something.
I would suggest that you work through the tests, the quizzes, and the homework, probably in that order. So, oh, duh. Sorry, guys. So mission 8 was on, come on, the antiderivatives, right? So there's a couple different things we did. The one thing was finding solution to initial value problems. And those are where we integrate, but we also have some kind of like, initial condition. So these are all kind of like that, right? And by the way, this problem, there are a few problems in here that don't make this problem. They don't. They don't make sense with f of 0, 0. 0 is not defined for the integral. All right, let me get to it here. So is there any particular questions in this that you'd like to look at? So if we have an initial condition, we anti-differentiate, and then we fit the constant to match the data. That's the big idea there for problem 301. I hope now that you go back to problem 302, you're just going through it and you're going, I can do this, right? Like these should be, each one of these should be like a 20-second do. Like no, certainly not more than like it shouldn't be more than a minute to do any of these, all right? Like what I'm trying to say is like the first problem on the math battle, you ought to be able to just go through there and just write down the answers one after the other. Except for that like x squared over x squared plus 1. Admittedly, that one, that would take a second. So what I'm trying to say is you need to make sure that you have down pat your basic integrals, right? Integral sine, cosine, exponential, a to the x, 1 over x, secant squared, secant tangent, cotangent squared, cosh, sinh. Don't make sure that you have clear in your mind the integral of 1 over 1 plus x squared is inverse tangent. The integral of dx over the square root of 1 minus x squared is inverse sine. We also had the inverse hyperbolic tangent as the integral of 1 over 1 minus x squared. We saw that as well later in this one. Make sure you know about, your professor is a bit of a mathematical prankster at times. He will do things like this, right? So watch out for sine squared plus cosine squared. It's just 1, recognize it as such. You guys did pretty well on these kind of reverse set up the integral problems. So I think it's likely I ask a question like this on the test where we have to do the definition of the integral and the right endpoint rule to work it out like this, problem 306A. Let's see here, what else can I tell you? This is FTC3 again. I would say also another thing to mention is you make sure you know what cosh and sinh are. Like cosh is 1/2 e to the x plus e to the minus x, right? Sinh is 1/2 e to the x minus e to the minus x. These are the definitions of cosh and sinh. Sometimes you need to know those. This here, what do you do when you've got x over x plus 1? Well, you just do algebra, right? 1 plus 1 over x. On the other hand, if I had x over x plus 1, it would be a little bit different. Oh, look, problem 318 was the problem on the math battle. Well, without the bounds, I think, but let's see here, what else to tell you? Let me skip to the end here. Oh, we're already at the end. Wait a second. I guess mission 9 is what we wanted to look at, isn't it? So mission 9 was what? I do like these even odd things. That even odd for a test question is really nice. Make sure you know about the integrals of even and odd functions like we talked about. And then of course use of, like probably 30-40% of your test is U substitution, something like that. Don't be caught off guard. If I ask you like integral of cosine cubed or sine cubed, can you do it? Here's supposedly. Like here's integral of sine cubed, for example. What we do is 1 minus cosine squared times sine, make a U equals cosine substitution, like so. So if you understand one of these carefully, you ought to be able to do the integral of sine cubed, sine to the 5th, cosine to the 5th, cosine to the 7th, sine to the 7th, like whatever odd power, sine or cosine, you could do it. It's just a matter of annoying algebra. What else can I tell you? Yeah. The rule on the bounds changing is you have to think through how the bounds change. So like if I've got U equals cosine theta, I plug in 0. Cosine of 0 is 1. I plug in pi, cosine of pi is minus 1. So that's why the bounds change from 0 to 1 and from pi to minus 1.
So once you make the U substitution, that's when you plug in.
Right. The rule is whatever you write for the differential, like the d theta has to be reflected in the bounds. That once I write d theta there, my bounds have to reflect theta bounds. Once I write du, these are the bounds for u. So the bounds match the differential. Like that is the rule. That's the rule. I mean, that's a theorem, but that's also a rule. Part C here, beware, we need to know that adding angles formula for the, not the double angle formula for like cosine squared or sine squared. Remember, we do 1/2. Oh? What? Dudes. That's a minus. Seriously. That is a minus. Whoa. Minus. But yeah. Remember, there's a minus in the double angle formula for sine squared. There's a plus for the cosine squared. And look, I got it right here. See? 1/2, 1 minus cosine 2 theta. That's better. Duh. If you've got an odd total number of sines and cosines, you can usually just make it by a U substitution. Net even number is annoying. We got secants and tangents. Either you're going to make a secant substitution or a tangent substitution usually. Which one you do depends on the pattern. Part G is nasty. That's just a nasty, nasty problem. You need to know the trigonometry we talked about in class to do this. If you don't know that trigonometry, you just can't do it. So there's the trigonometry using complex exponential, imaginary exponential stuff. And of course, there's hyperbolic analogs to everything. Anyway, I'm out of time, but I'll see you guys tomorrow. But yeah, we won't have class Friday. We won't have class Monday. I think Tuesday's the last day of classes, right? Next Tuesday? Isn't that right? Am I wrong? Am I right? I'm right. So next Tuesday is the next time. We'll meet next Tuesday, but we won't meet Friday, we won't meet Monday.